So welcome to lesson 2 on calculus, and today we will be focusing on the topic of sets. I hope you enjoy this lesson, and let's quickly jump into it. So a set is simply a collection of objects that themselves could be considered to be entities. And so within a set you have components, or you have individual items that we consider them to, we actually call them elements, or some people call them members. The symbol for something is a member of is this capital epsilon sign, such that if we say that x epsilon A, this is read as x belongs to A, or x is an element of a set A, and A here represents a set. Sometimes we could also say that x is in A, or A exists in A, right? In mathematics, we use the sign equal to mean a logical identity between two sets, for example A and B. So if we say equals to B, it means that A is B. Then I also say that a set is considered to be the same as a set A is considered to be the same as set B if and only if A and B have exactly the same members. So saying that A equals to B means using what we covered in lesson 1, this universal quantifier, that for all x's, this is what this sign means, for all x's, if x is a member of A, then x is also a member of B. And if we're to use the expression for this double-ended arrow, we would say for all x's, if x is a member of A, if and only if x is a member of B. Okay. Furthermore, some sets could be subsets of other sets, and we say that a set A here is a subset of a set B, or that A is included in B, or that B is a superset of A if every element of A is included in B. The symbol for inclusion is this elongated C here, such that we could say that if A is a subset of B, then we say A, this elongated or inclusion symbol, B, which means that, again, using the universal quantifier, for all x's, if x be a member of A, if x is a member of A, then x is a member of B, and that is straightforward. Also, we could also say that A equals to B if and only if A is a subset of B and B is a subset of A, and that is straightforward. Now, if you have 3 elements, 1, 4, 7, the way we combine that into a set, we have these curly brackets, and we have 1, 4, 7, close the curly brackets. If we have only one member in the set, we call it a unit set, and we still include the curly brackets around it. Sometimes we have infinite members, and the way we sometimes do that is by indicating the 3 dots at the end of the last member. For example, we have all the positive even numbers. This is 2, 4, 6, 8, and so on. Curly brackets around them. We could also use statement frames to define infinite sets, and the way we do that is we could say for x, given x, we have a set for which px is true. and this means really, if we express it this way with curly brackets around it, it means it's a set of all x such that px is true. In other words, if we have this expression, we are saying that this is a set such that if y be an element of A, or y be an element of A, if and only if P, Y holds. Another example is we could, instead of px, we have x squared less than 9. So if we have this expression, what this set really implies is that we have a range for which x, when squared, is less than 9. And that means this is an open interval between -3 and +3. And just using this expression here, we can do the same for what we saw here. Okay. Now, a frame px here is a property that an object x may or may not have, and so the set here is a set of all objects having that property. In other words, this set now picks the elements of x for which px holds. If px is never true, then it means that this set here is a null set or is an empty set. And if px is never true, we're just repeating the same thing here. If px is never true, then the set is null. So there's this very interesting topic called restricted variables, and in mathematics what happens is that a variable is not allowed to take all objects as values, right? So for example, a variable could be generalized to mean, for example, real numbers. Those are not all values, or it could mean even numbers, or it could mean all positive integers. Now, these variables can only take values that are members of a certain set, and that set is called a domain. In calculus, we mainly look at the real values as our domain. If you're looking at single variable functions, the domain is sometimes explicitly indicated, but it's often implied. You know, we are not always shouting, "Oh, x means real numbers." But also, if you're doing, for example, integration, you have bounds within which you're integrating. For example, n is usually used to specify an integer, and we could have such an expression where you say for all n, then pn, or for every integer n, pn. Another way of indicating it is by explicitly indicating that n is a subset of the integer set here, and we use this form of letter z to imply integers. We could have an expression like this that treats that there exists an n in z, which is a set of integers, such that pn, or there exists an integer n such that pn. These quantifiers that we have here are called restricted quantifiers. So these relations here do correspond. So if we have, for example, we have a universal quantifier of x, px, this is the same as saying that for all x's, if x be a member of n, then px holds. And then if you have this existential quantifier, px, is the same as saying if there exists an x, then the expression x is a member of A, and px is the same as what we have on the left hand side. And then using this set formalism where x is a member of A and then px is true, this is the same as, yes, x is a member of A, and at the same time px holds. So it's an AND relationship. Okay. Then we have what we call ordered pairs. So if you have these brackets and then we have a pair of values a and b separated by a comma, what this means is that if x and y are ordered pair equals to certain values a and b, then that means that x is equals to a and y equals to b. So the order really matters there. And that means that if we have an ordered pair of 1 and 3, it's not the same as an ordered pair of 3 and 1. So what that means is that there is a correspondence. There is a correspondence between x and y, and this is a pairing of objects such that any two objects, x and y, the pair x and y, either does or does not correspond. We've already talked about this, and then going forward, sometimes we have a statement frame px and y, and we talked about what a statement frame is. It's a frame that we cannot tell whether it's true or false unless we do put in values. So from transitioning from a one variable frame to a two variable frame, pxy, if it has two free variables with x and y corresponding, then it means that it does so if and only pxy is true. Now another thing that we're going to say is that a set of all ordered pairs xy of corresponding elements is called its graph, and we know what graphs are in elementary mathematics. So a collection of the x and y ordered pairs is called its graph. Since the graph of a relation is a set of ordered pairs, it is efficient and customary to take the graph to be the relation, right? We just have to highlight that a relation or a correspondence is simply a set of ordered pairs. And if R is a relation, then we say that X has a relation to Y. And how we symbolize that is as we have X, R, Y. And that is happens, or that is true if and only if X and Y are all elements of R. We also say that X corresponds to Y under R. That's another way you could put it. So we looked at what ordered pairs were, so a pair of x and y, and now if you now take the sets of only the first x's, the first items in the ordered pair, that is usually deemed the domain of of R, and it is designated as the domain of R. R being the relationship between x and y. And this is how you would express it. Where the domain of R is the x's such that there exists a y for which the relationship xy are elements of the relationship R. Now the set of second elements is called the range of R, and that is the y. So if you get a set of y's, that is R, and that's called the range of R. And the range of R is all the y's such that there exists an x for which the relationship xy are elements of the relationship R. The inverse also obviously means you're swapping x and y, so that y comes first and then x comes second. And this is how we've done it. So the inverse of R is that there exists x and y such that the relationship yx are elements of R. Another thing that we can say is that a segment frame px having two free variables actually determines a pair of mutually inverse R and S. So R and S are mutually, and these are called the graphs of P as follows. So that if we have R being the forward direction, X and Y such that Px all, S is the backward direction, we have Y and X flipped such that Px and Y holds. So one other thing we can say is that a two variable frame pxy together with a choice for which variables which variable is considered to be fast might be called a directed frame. There's another important concept, and that's the Cartesian product. So if you have a set A and B, its Cartesian product means that we are looking at a set of ordered pairs x and y, for which we have x being a member of A and y being a member of B. So you have, if you have, for example, 1, 2, 3 set A and 4, 5, 6 as set B, then the Cartesian product of those two sets is ordered pair of 1, 4, ordered pair of 1, 5, ordered pair of 1, 6, ordered pair, and then the set is continuing, ordered pair of 2, 4, ordered pair of 2, 5, ordered pair of 2, 6, ordered pair of 3, 4, 3, 5, and 3, 6. So that is the Cartesian product. It's a set of ordered pairs such that if we have x, A and B being considered for the Cartesian product, then x is a member of A and x and y is a member of B. A relation R is always a subset of the domain of R times the range of R. So that's the Cartesian product of domain of R and Cartesian product of the range of the Cartesian product of domain of R and range of R. And we know domain is a set of x's and range is a domain is a set of x's and range is a set of y's. If the two spaces are the same, we can use the exponential relation notation a squared. In other words, for the sake of, let's say, R here, we'll just say R squared. The Cartesian product R squared is R by R, which is the usual analytic plane for which we play around. And this is an example. So if we have A being the set from here to here, and also set from here to here, and then B being set from this and this, and then at this point here, the Cartesian product here is simply the domain here, the line here, the line here, because this is just a point, and the domain here, right? So that is just an expression of what a Cartesian product of two sets is. So interesting thing, we could also say that if R is a relation and A is any set, then the restriction of R to A, or we can say R, this vertical line, A being a set and R is a relation, is a subset of R consisting of those pairs with the first elements being in set A. And how we would express it in a set format is that the restriction of R to A is this set of x and y ordered pairs such that x and y is obviously the elements of R and x is the element of A. If R is a relation and A is any set, then the image of A under R, and how we express that is R, the square bracket A, is a set of second elements of ordered pairs in R whose first elements are in A. Okay, and I would express that is suddenly the image of A under R is a set of A's for which there exists an X such that X is an element of A, and also the XY combination or XY ordered pair are elements of the relation R. In other words, the image under R is the range of the restriction R to A. Let's talk about functions and mappings. A function is a relation F such that each domain element X is paired with exactly one range element Y, right? The property can be expressed as the ordered pair xy is an element of the function f, and also if we have xz as being the element of m, then automatically what we're seeing here is that y should be equal to z. So the y, which is thus uniquely determined by f and x, is designated as fx. If we have an element fx which you plug into the function f and you get a value y, y can be the same as, can be represented as fx. And so we say that if y is equal to fx, if y is equal to fx, if and only if the relation xy is a member or element of f. Let's take an example, f that transforms x to x squared. Then the inverse is not a function because f1 contains 4, 2 and also 4, negative 2, and so is not a function. F inverse is not a function. If f inverse is a function, we say that f is a one-to-one, and thus f is a one-to-one correspondence between its domain and its range. We'll have a specific word for which we use that relationship, where there is a one-to-one forward and backward relationship. Another thing, we could also say that each x is an element of the domain of f that corresponds to only y being equal to, y being an element of the range of f. F is a function, and each y is an element of range of f that corresponds only to one x being an element of the domain of f. In that situation, f inverse is a function. Now, if we have a function f that transforms a set A to set B, that can be read as function of f from A to B, where the domain of f is equals to A and the range of f is a subset of B. So looking at the function f could also be called a map or a mapping or transformation. Some important keywords that we would like to note is that a mapping f of A into B is said to be injective if f is one-to-one. That means that two x's or two different x's, x1 and x2, cannot map to the same item in the B, in other words, in the range. So there is just one-to-one. It's like you have a thread joining one element in the domain to one element in the range. For example, x squared has both negative 2 and 2, a positive 2 mapping into 4. So x squared is not an injective relation or an injective function. But a function, for example, fx 2x plus 3 is an injective because for every x across all the x's, you have one output that are not the same with the other outputs. There's also another thing that we could say, if the mapping f A into B is said to be surjective if the range of f is equals to B. In other words, there exists or all the items in the range have a corresponding item in the domain. There exists an x for which all items in the range have a relation f and to f that transforms x to y. If a relation or a mapping is both injective and surjective, we say that relationship is bijective. So that's the end of this lesson number 2. I hope you had something to learn from it. Until next time, bye bye.